All right, so that's a type 3 piece. And you see that there's another type 3 piece as well, which is C7 to C8. Those don't show up in the formula for capital G. There are no terms corresponding to type 3. Or you might say it differently. You can say that all the terms for type 3 are just zeros, and they just don't show up. Okay, so here's what you do. The easiest ones to work with are the type 2 ones, because what you're doing there is you're just taking the value of f at this endpoint, take the value of big F at this endpoint, C4, and then subtract away the value of f at this endpoint, C3. That change, let me call it like delta F4. So it's the change in f from C3 to C4. That is one term of the sum for G. You see, it's this term here. You evaluate big F at the right endpoint of that interval, then you evaluate at the left endpoint. And so that's like delta F sub n. Oops. Okay? And you'll similarly have this delta F sub 5, which is the change in F between C4 and C5. Those two are just included as terms of the sum. Now, the type 1 terms are not that much harder to understand. The good way to think about it is that instead of going all the way from C1 to C2, which would be exactly delta F2, we just stop short. We go from C1 to this point here. And that term is going to be included as one of the terms in the sum. But you see that this little piece is left out. What color should I use for this? Let me just do it in black. Okay, this little piece here is left out. There's nothing in the sum corresponding to that tiny little interval. So what is this point? If I project this point downward to the x-axis, like this point here, is phi sub 2 inverse of y. You see that it's part of the graph of phi 2, this being the graph of phi 1, and this green piece here being the graph of phi 2. So it's in the domain of phi 2, but it's the point in that domain where when you plug it into phi 2, it gives you y as the height. Phi 2 of phi 2 inverse, they cancel out. So see, that's exactly what phi 2 inverse of y looks like. It's that very point. And what we're doing is we're going from that point, we're like evaluating big F at that point, and then subtracting away. So yeah, you have to evaluate big F at that point. Then you also have to evaluate big F here at C1, and you subtract those two. So it's also like a change in F, but it's not a change in F, excuse me, all the way from C1 to C2. Rather, it's just a change in F from C1 to phi 2 inverse of y. And that's the term you're going to get here, for instance. Right, you see that you have f of, let's say, phi 2 inverse of y, and then f of C1. You subtract away. That's going to be the expression for all the green pieces. That's the expression that goes in there for all the green pieces. Now, what about the red pieces? Okay, let's go back to the picture. So let's look at a typical red piece. Well, a type 1. We have to look at a type 1 red piece. So let's say this piece here, phi 3. All right, so again, there's this special point on the x-axis, which is phi 3 inverse of y. Because that's the point on the x-axis, such that if you plug it into phi 3, you get y as the height. Okay, and what we want to do then is we want to actually take this contribution from that point to C3, leaving out this little bit here. So we're going to evaluate f at C3, and then subtract away its value at phi 3 inverse of y. Okay, now you see that that's exactly the term you have here. You would have something like f of C3, right, minus. Now there's a little twist, is that it's f upper minus, but basically what goes in here would be f3 inverse of y. That's what you would do with the red pieces. Now why the upper minus sign though? Okay, I'll tell you the answer to that in a minute. But roughly speaking, you see that's what you're getting, is you're summing up all of these yellow contributions, which are the full change in f from one endpoint to the other. Right? Then you have another change in f between C4 and C5. Okay, so you sum all of those up. And those correspond again to the intervals where the corresponding pieces of the graph, phi 4 and phi 5 in this case, are fully below the height level y. Okay. Then for these other type 1 pieces, when you have an increasing piece, you're just going to take the change in f from the left-hand endpoint of your interval to the point where the function crosses that line, leaving out the rest of that little interval. So that goes unaccounted for. Right, then for the decreasing pieces, for the red pieces, you're going to go from that point where the curve crosses that horizontal line toward the right-hand end and take that contribution. Meaning the change in f. Always, for every one of these little intervals, whether it be these yellow ones, or whether it be this green one, or whether it be this little red one here, for every one of those intervals, what you're calculating is the change in f on that interval. F at the right endpoint minus f at the left endpoint. And then you're summing all of those up. Okay. Now with that understanding, it's very easy to see that all these properties are true. If we keep in mind that visual understanding, because let's recall properties that we know about big F. Remember, big F is known to be a CDF. So we know that it's non-decreasing. We know that it's exhaustive. We know that its values, it's also right continuous. And we also know that it's valued in the closed interval 0 to 1. Okay, so notice that the fact that it's non-decreasing is going to tell us that every time we evaluate the change in f, these changes are always non-negative. Because we're always moving rightward on the number line. We're always jumping rightward. So when you make an increase in the input, the change in f can't be negative, since f is non-decreasing. So all these things we're adding, including, by the way, this change in f here, on that green jump, because again, it's a jump in the forward direction. And also this little change in f here in the red, because again, it's a jump in the forward direction. So we're adding up a bunch of positive terms. And that clearly tells us that g, the values of g, are non-negative, since every g of y is just a sum of non-negative terms. So g of y is definitely non-negative. Now I claim that also g of y is at most 1. And let me explain how I know that. What's the most I can ever get from this process? It's the biggest answer I could ever hope to get. Well, the biggest answer would be when there's none of these little things, like this one here, or this one here, which would be unaccounted for. These little question mark intervals. Because you see, those question mark intervals are not used. So it represents a wasted opportunity. If I did use those, I would have additional non-negative terms, because I could take the change in f. Now, granted, f might not change by very much on that tiny little interval, but it's still making a positive change, or a non-negative change, which could be positive. So by leaving out those intervals, by not using them at all, means that you're sacrificing an opportunity to gain an additional positive term. So like the best case scenario to make g of y as great as we can possibly make it would be to have none of those little question mark intervals. But then what we'd be having is the following. So right here, like g of y is at most the sum of the changes in f over just all values of n. From 0, 1 really, it starts at 1 because we're jumping from c0 to c1, that's like the first, it's n equals 1. Oh yeah, so from n equals 1 to like, big N plus 1. But what is that? That's just going to be f of c big N plus 1 minus f of c0. It's a telescoping sum. By these changes, what I mean is f of cn minus f of cn minus 1. So see that telescopes. Now, what does this actually mean? It just means f of plus infinity, which is cn plus 1, minus f of negative infinity, which is c0. And by exhaustiveness, f of plus infinity is 1, f of negative infinity is 0. So you see that the most g of y could ever be is 1. And that proves that the range of g of y is fully contained in this interval. All values of g of y are fully contained in that interval. Okay? Now, we can also easily see now that g is exhaustive. Because let's ask ourselves what happens as y increases. If we take this horizontal blue line and just make it increase in height, push it upward kind of forever, gradually, right? So try to visualize that blue horizontal line kind of moving gradually upwards with no bound in its height. So eventually we'll get high enough where it only ever intersects the two end pieces, if at all. See, once the blue line is high enough, like let's say all the way up here, it still intersects this piece because this piece is unbounded. This leftmost piece here just happens to be unbounded. And so every horizontal line, no matter how high up you push it, we'll cut that one. But actually the other end, the right-hand end from C7 to C8, doesn't even cut that anymore because of the horizontal asymptote. The blue line is higher than that horizontal asymptote. Okay, so see that the only two pieces that could potentially intersect that line, once it's high enough, are the two ends, and not even the two ends both have to intersect that line. So what's going to happen is all the intervals are going to be of the type 2, the yellow, this yellow type, eventually, except the two end intervals. The two intervals involving, negative infinity and plus infinity don't have to be type 1 intervals. But in that case, like if y is really, really high, so let me just write something down here, for very large y, much, much greater than 1, let's say, basically g of y is going to be exactly that same telescoping sum that we just wrote down, except the two ends may be missing. So you're going to have like this telescoping sum, which is going to have like cn to c1, okay? But then there are two other terms, which, now there are various combinations of what could happen. I'm just going to write down one case. There are several cases, right? Because there's like 4 combinations of things that could happen. But just to write down one case for you, we could have like f of c1 minus f of phi 1 inverse of y, which would represent this picture here, where the height y is like this large height, much, much greater than 1. And what I'm doing is I'm going from phi inverse, I'm a little bit wrong about that, I guess, because it's a decreasing piece. Is that right? Yeah, no, this is correct. The only problem with it is that I'm missing the upper minus. Yeah, so let's recall that first piece was a decreasing piece. It just so happens. So I said 4 combinations, but I'm wrong about that. There are actually more combinations because not only does it depend whether the two ends are unbounded or have horizontal asymptotes, but it also depends whether the two ends are increasing or decreasing. And there are already 4 combinations for those. So I guess we have 4 times 4 possible combinations. But I'm just illustrating the one that's in this picture. Let me just illustrate, to be definite, the case that's actually pictured here with this large value of y. Okay, so the formula was f of c1 minus f upper minus at phi 1 inverse of y. Okay, and then there's also a term corresponding to the other end, the right-hand end. But because the right-hand end is now a type 1, that term is very simple. It's just going to be f of plus infinity, in other words, cn plus 1, minus f of cn. And that's only there because of that horizontal asymptote. On the right-hand end, because we have this horizontal asymptote, once y is large enough up here, that last interval from c7 to infinity is going to be of type 1. It just so happens. It doesn't have to happen, but it can. Okay, so now you see that things will simplify. First of all, this term is just f of plus infinity, or 1. We also have a plus f of cn and a minus f of cn. They will cancel. And we also have like a plus f of c1 and a minus f of c1, and they will cancel. And so what's left is just 1 minus this last term there, or the 1 comes from here. And it's like f upper minus of phi 1 inverse of y. All right, now we're just going to ask, what happens to this as y goes to infinity? Now, let's let y go to plus infinity. And what happens to this? Okay, well, by the very nature of the picture that we're in, right, if we let y keep climbing, this point on the x-axis, which is phi 1 inverse of y, is going to go to minus infinity. As y keeps going higher and higher, that point is just going to keep moving further and further left, all the way to plus infinity. So that, in other words, this input is going to minus infinity. And we know that capital F is a CDF. So if I let its input go to minus infinity, then it goes to 0. And the same is true of f upper minus. Because f and f upper minus are basically identical functions. They only differ at jump discontinuity points. Right? The f and f upper minus basically have, like, at every jump discontinuity, they have their filled-in circle and their open circle swapped. But other than that, they're identical. The graphs are identical. So if one of them tends to 0 in the long run, as you move leftward, then the other one has to do the same as well. Okay? So what that's going to tell you is that this tends to 1 minus 0, or 1, as y goes to plus infinity. Okay, so if I let y go to positive infinity, then g of y is going to approach 1. In short, we have this equation. Okay, and then very similarly, you can prove that the other thing is true as well. G of minus infinity is 0. Okay, so I didn't actually give you the argument for this one, but it's very, very similar to what we just did do. Okay, so that shows that g is exhaustive. Okay. What about the non-decreasing? How do I know that g is non-decreasing? Okay, well that's also not too bad if you just look at the picture and think about the geometric interpretation, graphical interpretation. The idea is that if I increase the y value at all, let's say I just increase the height of this line by any amount. So I take that horizontal line that's currently at height y, and I pick it up and make its height y plus epsilon, where epsilon is positive. I claim that the capital G function can only ever increase or stay the same if I do that. So if I increase the y, which is the input of capital G, let's say from y to y plus epsilon, where epsilon is positive, then the g of y itself is going to either stay the same or possibly increase. And it's very easy to see why this is true. So first of all, the yellow terms are going to be totally unaffected, because if the blue horizontal line is already above all those pieces, then when you pick it up even higher, it's still above them. So those like yellow terms, like this delta f4, delta f5, they stay fixed as you do this, as you increase the y. The terms that change are the type 1 terms. But how do they change? Well, look, if you pick up the line even higher, you see what happens is that the green interval here just gets longer, which means the change in f gets bigger, because f is non-decreasing. And the red interval here, this red interval also gets longer. Right? When you pick up that blue line higher, it just lengthens those green and red intervals, makes them longer. When you make an interval longer, then a non-decreasing function like f will have a greater change, greater or the same. So yeah, those terms are only increasing as well, or possibly staying the same. So it's clear that g is indeed a non-decreasing function. Okay? Then finally, the right continuity is quite easy, just from the formula itself. If you just stare at this formula a little bit. So if I let y increase, which is what right continuity is like, right continuity is where should I write this? Hold on. Let me write it in red down here. Okay, with right continuity, the only thing that matters is that y is approached, let's say by some other variable v, from above. Right? V is going to be like decreasing to y. In other words, v approaches y from above. And the question is, what happens to g of v? G of v should then approach g of y. And that's the question, does it? If I let v decrease to y. Okay, so v is greater than y. That's the intention here, is that v is greater than y. And we know that, okay, if v is greater than y, then v is also greater than the range of phi n, because y is already greater than that range. So those terms all stay the same. Those terms don't change if I change y to v. If y jumps upward to v, then yeah, these terms stay exactly the same. There's no change in any of these terms at all. The only change that takes place if I let y jump upward to v, the type 1 terms are going to change. But the question is, how do those type 1 terms change? Right, well, look, each type 1 term just consists of a continuous function of y. Right? Remember that phi n inverse is always continuous. In fact, it's always differentiable on the interior of its interval. Continuous on the entire interval. So phi n inverse of y is a continuous expression on the entire domain of phi n inverse. And what are you plugging it into? Well, you're plugging it into a right continuous function. See, f itself is right continuous. So you're plugging a continuous function, phi n inverse of y, into a right continuous function. And it's pretty obvious that that's going to yield also a right continuous function. Remember that a composition of continuous functions is continuous. In a very similar way, if you take a continuous function and plug it into a right continuous function, you get a right continuous function. Okay, because the inner function presents no difficulties. It has perfectly good behavior under limits. It's continuous. And so, yeah, the right continuity of the outer function then dominates. And the whole thing as a function of y is therefore going to be right continuous. Okay? So this expression here as a function of y is going to be right continuous, and then you're just subtracting a constant. You're subtracting from that f of cn minus 1. Now if you have a right continuous function and you subtract a constant, it's obviously still right continuous. That takes care of the green terms, right, the increasing terms. But what about the red terms, the decreasing terms? So there it's a little different, but also very, very similar. You see this inside expression here is continuous, C0, on its entire domain. But what are you plugging it into? Okay, well, I claim that if you include this minus sign here, you're actually plugging it into also a right continuous function. And that's the reason for this upper minus. Because f upper minus is left continuous, but then when you negate it, you're making it right continuous again. If you think about that graphically, when you take the graph of a function and you negate it, it reflects the graph over the horizontal axis. It takes the whole graph and reflects it over the horizontal axis. So that means that the filled-in circles, originally, the function f has its filled-in circles above, but then that's f, right? F minus, though, has its filled-in circles below. But when you negate that, you look at its reflection, you see that's minus, that's like minus f upper minus. That has its filled-in circles above again. Okay, now you might stare at this picture and feel really uneasy, because, isn't it supposed to be like a non-decreasing function in the end? This g is supposed to be a non-decreasing function of y. So why am I getting a picture that looks like it's trending downward? So yes, the upper circle is above, the upper circle is filled in, but it looks like it's trending downward. And it is, but the thing is that it's not just f upper minus, or negative f upper minus that you have here. It's negative f upper minus with this thing plugged into it. And that thing, remember, is decreasing. So you see that you're like plugging a decreasing thing into the input slot. So the input slot is not being read left to right. So it's true that this is downward trending if you read the input left to right. Then the function falls. But if you read the input right to left, then it's increasing. And that's what's going on, because the thing that's being plugged in there is phi n inverse of y, which is a decreasing function in this case. This is the decreasing case. So it's kind of reading the input to that function backward, from right to left, giving you an increasing function, and the upper circle is the one that's filled in, and the lower circle is. So that's actually a right continuous piece, and then you're just adding a constant to that. So in either case, whether you have a green piece or a red piece, as a function of y, the corresponding term, the corresponding type 1 term, is a right continuous function of y. And again, these terms down here are totally unaffected. So they give also a right continuous function, namely just a constant function. So that shows that g of y is a right continuous function of y. Oh, where am I here? Sorry. Yeah. Okay, and with that, we've fully checked that indeed this capital G is a valid CDF, and therefore it determines a random variable. And that's the random variable that we're calling phi of x hat. Now, where does this formula come from? Well, already in this picture, you kind of get a clue as to why we would call this phi of x hat, but I'm going to do a formal calculation, show you where this formula comes from. Okay? The idea, remember, is that we're supposed to be calculating, like, what is the CDF anyway? In principle, it's supposed to give, and I'll ask this as a question, because I don't want to presume that it does give it, I want to prove that it gives it. But yeah, g of y is supposed to give the probability that this new random variable acquires a value less than or equal to y. Okay, so we can start out by trying to calculate this probability according to the rules of probability, and seeing if we get that big nasty formula, which is by definition g of y. And then we can say that these two are equal. So that gives the correct probabilistic relationship. Right? Remember, G is a valid CDF we just showed, and therefore it corresponds with a random variable. And if I call this random variable y hat, right, meaning I just define phi of x as that y hat, right, phi of x hat is simply defined as that y hat, then this probability here is by definition simply the probability that y hat is at most y. Because phi of x hat is simply a notation that stands for y hat, nothing else. So this is literally what it is. And then the question is, does this relationship hold? Are these two quantities equal? And indeed they are, because that's exactly the probabilistic relationship between a CDF and its random variable. Every pair, every associated pair of a CDF and a random variable has that probabilistic relationship. So this would be no exception. Okay, but so let's go ahead and do that. We're going to try to calculate using the rules of probability theory. Now this calculation is necessarily, how should I put it? Let me say that it's like an aspirational calculation. What I mean by that is that, strictly speaking, we don't know what this thing is until we've completed this whole process. So I'm going to proceed as if I understand what that is, just for the purposes of discovering the correct definition of G. This is not a proof of anything. This is kind of a discovery process, let me call it that as well. We're not proving anything here, because G has its own definition, sort of logically independent. The definition that I gave for G was logically independent of this proof. That definition makes perfect sense and stands on its own right. We did check that it is a valid CDF. That is a theorem. We just went to a lot of trouble to prove that theorem. And we know already from prior theory that every valid CDF determines a unique random variable. And we're free to call that random variable phi of x hat if we like. The question we're trying to answer now is why do that? Why call it that? So it's a purely motivational question. We're not trying to prove any sort of theorem. We're just trying to say, like, how did we discover the right formula? Surely that formula must come from someplace, right? So this is really more of a kind of discovery process or a heuristic argument. So it's not to be interpreted as a formal proof of anything. And that's because, again, we don't really know what this symbol stands for yet until we fully complete this process. All right, well, with that in mind, we can say something like this. We can say whatever this thing stands for, it should be true that if I take this event, whatever this event actually is going to turn out to be, we don't really know yet, but supposing this is an event, we can intersect that with the union of all of these events. The event that x hat falls into the nth interval. And I'm going to label them so that it's closed at this end, it's closed at the right hand end, and open at the left hand end. The reason I want to label them that way is because I want them to be disjoint sets. I have these points, and I want the intervals to be disjoint, so I'm going to consider it open at this end and closed at this end. And then the next one will be open at this end and closed at the other end. So these intervals are pairwise disjoint with that convention. And then I'm just going to take the union over all the subscripts. Okay, so why does this work? Well, look, the union of all these events is just the full sample space. Because every possible outcome of the experiment, every possible outcome little omega in the full outcome space, has the property that x hat acquires some value, and that value has to belong to one of these intervals for at least one n. At least one value of n. And therefore, that is going to belong to the union over all values of n, right, of these intervals. And, okay, reason is because that union is just the reals. Remember that we're including negative infinity, and we're also including positive infinity. So the union of all those intervals is just the full real line. And obviously the outcome of the experiment does indeed fall into the full real line. So you see, when you intersect any event, let me call this event temporarily E. If I intersect that with the entire sample space, that's just E again. E intersecting with the whole sample space is just E again. And that's because E is a subset of the sample space. So it's correct to write it this way, okay? And then by set theory, simple set theory, we can take this expression, including the intersection sign, and just distribute that into the union. It's like a correct law of set theory called the distributive law. Basically says that, intersections distribute over unions, and conversely, unions distribute over intersections. So that's going to express the thing this way. It's going to be the probability of the following union, where x falls into this nth interval, and at the same time, phi of x hat is less than or equal to y. So this is an intersection. I'm just writing it with a conjunction. Let me put an explicit conjunction. Right, when you have the intersection of two events, if you have an explicit description of that event, and then an explicit description of the other event, you can just write that as a conjunction. That's what I'm doing here. Again, you take the union over all the subscripts n. Now notice that these are pairwise disjoint, as n varies. In other words, if n and m are two different subscripts, then the event that x falls into the nth interval, and some additional thing happens, is completely disjoint from the event that x falls into the nth interval, and that additional thing happens. And that's simply because this interval and this interval are already disjoint. The way I label the intervals, if the subscripts are distinct, and because I included one endpoint and not the other, these are pairwise disjoint, as long as the subscripts are different. So you see, x hat can't fall into both of them simultaneously. So regardless of what this other restriction is, this other restriction doesn't even matter. Since x hat cannot simultaneously fall into both of these intervals, these two things are disjoint, meaning that their intersection is empty. So this intersection here, I have no room to write it. So let me erase this. Oops, it is empty. They have nothing in common. So these are pairwise disjoint. And remember that the probability of a union of pairwise disjoint sets, this is like the finite additivity, so I'm using the Kolmogorov axioms now, which already should tell you that this is not a rigorous argument for us. One of the Kolmogorov axioms is countable additivity. But we're not even using the countable part, because for us there's only a finite number of these intervals. We're really just using finite additivity. Meaning we have a finite number of pairwise disjoint events. We just have a finite number of them. But anyway, the fact that we're appealing to the Kolmogorov axioms should already tell you that this is just an aspirational argument. Because remember that the whole point of this approach to probability theory is to avoid the need for like the Kolmogorov axioms in detail. The only purpose of studying those at all was to understand why like the three key properties were necessary things to include in the definition of the CDF. Okay, so that's important for that reason. Obviously, the whole theory would look totally unmotivated and wild and like out of left field if we didn't understand the need for the three key properties. So we have to have some familiarity with the Kolmogorov axioms, obviously, but we're sort of constructing a theory of random variables that totally avoids the need for detailed probability theory. So but remember that this is not a proof of anything. This is just an attempt to understand where that formula came from for capital G. All right. So anyway, using countable additivity, or really finite additivity in this case, this probability can be broken up as the sum of the individual probabilities, where x hat falls into the nth interval, and phi of x hat is at most y. Okay, and now, starting from there, you see that we can distinguish those terms where y is in the range of phi n, and it's the same expression. And then those terms, where y is above the range of phi n, it's the same expression. All right, and then there's actually additional terms where y is like strictly less than the range, and it's again the same expression. Okay. But you see, all of these probabilities are going to be zero, so we can just leave out all of these terms actually. Okay, let me explain why these probabilities are zero. It's because if you look at it, this event has to happen. X hat acquires a value, you plug that value into phi. Right? So that's what's going on here. Is like x hat acquires a value when you do the experiment. You're then taking that value and plugging it into the function phi, and we require this to happen. So that cannot happen when y is less than the range. You see? Maybe I should draw a little picture. So we're looking right now between Cn minus 1 and Cn only. And let's just say that piece happens to be like one of those increasing pieces. And let's say that y is less than that range entirely. Okay. So we do the experiment. X hat acquires a value, which is x hat of omega. We plug that value into phi. And we're also assuming, by the way, that that value, x hat of omega, is in this interval. X hat of omega has to fall into this interval first. Otherwise, this term would not be relevant. So yeah, so x hat of omega is somewhere in this interval. And then you plug that into the function phi, and you get this height. Now, can that height satisfy this inequality? Less than or equal to y? No, because the height y is actually below that entire piece of the function. So therefore, these two things cannot happen simultaneously in those cases, when y is less than that range. So since the two things cannot happen simultaneously, their conjunction is like always false. And that event is just the empty set. So this really just boils down to the probability of the empty set, and that is indeed zero. So you see that the type 3 terms just disappear. That's what these red bracketed terms are. The type 3 terms, they just disappear. And that's going to leave us with type 1 and type 2 terms. Okay, now going further, the type 2 terms can be simplified. Because in the type 2 terms, this can be ignored. This inequality can just be deleted. And we can write the entire expression as the probability that x hat falls into that interval. That's it. Okay, now you see why that's true is because in the type 2 terms, the picture looks like this, where let's say I have this interval, and I have, let's just say it happens to be a red piece. But the height level y is above. That's what the type 2 situation is. The height y is above the full range. So when the experiment acquires a value, omega, and we plug that omega into x hat, you're going to get some value in this interval. And if you then plug that into the function phi, you get this height. Now, is that height less than or equal to y? Yes, necessarily. It has to be. There's no choice. So that condition can actually be ignored because it must happen. No matter where x hat falls in this interval, because the height y is high enough, above the entire range of that piece, phi of x hat will necessarily be less than or equal to y. So it adds nothing to include that condition. It just adds nothing. Changes nothing. Okay, and therefore we can just write that term this way. Now you see, this probability already we know how to calculate. That's just the probability, it's big F of Cn minus big F of Cn minus 1. Those are exactly the type 2 terms. I'll remind you, this was a strict inequality here because the interval is open at that end, and this one is a weak inequality because the interval is closed at that end. But remember how this works is that it's like the probability of this minus, let me slow it down slightly. It's basically this event minus this other event, both with less than or equal to, because you're getting rid of all the outcomes where this inequality is true, and all that remains is outcomes where this opposite inequality will be true. Okay. And then just by the subtractivity of probability, we get the probability that that is true minus the probability that this is true. Okay, now this one is just the CDF of x hat evaluated at Cn, and the other term is exactly the same, the CDF of x hat, but just evaluated at Cn minus 1. So that's again the change in f, like the nth change in f. Okay. So those are the type 2 terms, they're very easy. Now, that argument should also tell you how the type 1 terms are dealt with. It's basically the same, it's just that when you look at these two conditions together, so let's just take a look at the upper limit on x hat. This first condition here involves x hat being less than or equal to Cn, but in the case where phi n is increasing, by the way, I should also mention that, I should do this on the next page. So our expression for this probability has boiled down now to the following thing. You have these type 1 terms where y is in the range of phi sub n. And this probability now is going to look something, I'm going to change it to look like this. So first of all, of course, we have to have these inequalities. But also, instead of writing phi of x hat is less than or equal to y, I can now write phi n of x hat is less than or equal to y. The reason is because phi coincides with phi n on their common domain, which is this interval. And since x hat is known to be in that interval, that's the only relevant interval. Right? It's x hat that's being plugged in, and x hat is known to be in that correct interval. So phi and phi sub n coincide in that interval. Therefore, you can label it as phi, or you can label it as phi n indifferently. Okay. But and then you have the type 2 terms, which we already know look something like that. In other words, now. Good. Now, let's again distinguish between the terms where phi n is increasing. And let me just look at that one first. Let's suppose that phi n happens to be strictly increasing. In other words, phi n prime is strictly positive on the interior of the interval. Okay, in that case, there are going to be two upper limits on x hat. You see, on the one hand, x hat has this upper limit, but on the other hand, you can just take phi n inverse of both sides of this. Basically apply phi n inverse to both sides. Right? And because phi n inverse is increasing, it preserves the inequality. You can just take phi n inverse of both sides, and the inequality here will be preserved. Because increasing functions preserve inequalities when you apply them to both sides. That's in fact the definition of an increasing function. It preserves inequalities. So what that gives is that x hat is going to be less than or equal to phi sub n inverse of y. So you see you have these two upper limits. But which one is the sharper one? Which one is the stronger statement? Well, it's this one. This limitation supersedes the other one, because phi n inverse of y is somewhere between cn minus 1 and cn. So saying that x hat is less than or equal to this one will automatically imply that x hat is less than or equal to cn. So it's the stronger one that dominates. And therefore, what we end up with is just the probability that x hat is greater than cn minus 1, but less than or equal to phi n inverse of y. And you see that is also of the form big F of the right endpoint minus big F of the left endpoint. And that's where that type of term comes from. That's the type of term you get when you have one of these increasing pieces. Right? And I'll just leave it to you to verify the other type of term that you can get when you have a decreasing piece. When you have an n for which phi n has a negative derivative on the interior of the interval, then in that case, the correct, then you have to look at the lower bounds on x hat. See, we looked at the two possible upper bounds, and we chose the sharper of the two, the stronger. But in the other case, you have to look at lower bounds on x hat, between cn minus 1 and phi n inverse of y. And the stronger statement there is this one again. But because it's a less than or equal, that's why you need the upper minus to get the correct value, to get the correct type of term. Remember the correct type of term in that case is where you have f of cn first, and then you subtract away f upper minus of phi n inverse of y. Why do we need the upper minus? Well, it's because the inequalities we're going to get here look like this. The lower limit is going to be phi n inverse of y, but it's a weak inequality now. And the upper limit is also a weak inequality. Now, when they're both weak inequalities, that's when you need one of those upper minus signs. Oops, not inverse, but upper minus. Okay, and so that's going to be the correct term for those cases. So there it is. That's a complete derivation. All right. So in this derivation, what was the meaning of this expression? Which is only temporary. It's like basically we're just temporarily giving it a meaning, just long enough to do this derivation. And then once we see what the capital G should look like, we can then just independently make that, the definition. We just take that G. We know it's a correct CDF because we verified that independently, and therefore it corresponds to a random variable. And then we can make that random variable the new meaning of phi of x hat. But what's the old meaning? In this derivation, we have an old meaning, and then later we replace it with this new meaning, where we take the G, which we know is a CDF, and we take its pseudo inverse. That becomes the new meaning of phi of x hat. In other words, it's the random variable associated with G. Okay, but the old meaning here is like this. It's basically a function. So here's the old meaning, temporary meaning. Okay, it's a function from the open interval 0 to 1 into the reals, which takes a given omega as the input, and what it gives out is phi of x hat of omega. Because remember, that was the reasoning, is that we do the experiment, so we get some outcome of the experiment, which is some little omega in that. It's like a point on our dartboard. We're thinking of probability as consisting in an experiment where we throw a dart at a one-dimensional dartboard, stretching between 0 and 1. So let's say we throw the dart, we get a particular outcome, omega. Then we plug that into x hat, and that's the value acquired. But then we plug that into phi to get the value acquired by this. So in other words, what this is composition. It's like the composition of these two functions. Phi composed with x hat. That's the temporary meaning. We give it that meaning just long enough to figure out the correct formula for capital G. Once we know the correct formula for capital G, we independently verify that it is a valid CDF, which we did. And then we know that every valid CDF determines a random variable, and we just call that random variable phi of x hat. So we replace this older meaning of composition with the new meaning. You take your G, pseudo-invert it, and restrict to the open interval. Okay? So in the end, that is really our technical definition of phi of x hat. Okay, great. So anyway, that defines one random variable as a function of another. That's the definition. At least for nice functions, well-behaved, nice functions of the kind I described, such as x squared or x cubed. Okay, that gives a meaning to something like x hat squared or x hat minus its own expected value squared if it happens to be expectable. We now know at least what these mean. We can calculate the CDF of this thing based on the CDF of the original x hat. Given the original x hat through its CDF, we can use that CDF to construct this G, and then pseudo-invert and restrict to the open interval to get x hat squared, let's say. And we have to use this construction that we discussed to construct the G. Okay? Actually, it's very very instructive to carry out this process just one time for practice. Let's just do a quick example. And of course, the example I'm going to choose is exactly the function of the moment, which is x squared. I'm focusing very much on this function x squared, or more generally x minus a constant squared, simply because that's the thing involved in variance. We have to take the expected value of x hat minus a constant squared. That constant happens to be the expected value of x hat, assuming that exists. But that means I have to understand this as a random variable. And hopefully it's an expectable random variable, so we can take its expected value. That's going to give us the variance. So yeah, that's why I'm so focused on the function x squared, or x minus a constant squared. So actually, let me do that. X minus alpha squared, where alpha is some real constant. Okay, so given f, given that x hat has a CDF, which is big F, that's given to us. We have no choice about that. But what's the G? We want to construct the G. So remember that our function is going to look like this. It has this decreasing piece up to alpha, and then it has an increasing piece the rest of the way. So it's going to depend whether the height y, like this given y, is non-negative or negative. There's a case when y is greater than or equal to 0, and then there's this other case where y is negative. Okay, so let's already distinguish between those two cases. And I'll put the case where y is negative on the bottom line. Yeah, so in that case, you can see that the answer is 0, if y is strictly negative. Okay, and it's because there are no type 1 terms, since that horizontal line does not cut through either the red piece or the green piece. But also, that horizontal line is not above either the red piece or the green piece. It's actually below both of them. So that's just, there's only type 3 terms in that case, and all the type 3 terms are 0, so they add up to 0. So now we can focus on the other case where y is greater than or equal to 0. Okay, and in that case, first of all, we can easily calculate like the local inverses. Basically, this piece is phi 1 of x, where x is like up to alpha. That's the domain. And what's its inverse? Phi 1 inverse of x is going to be, well, we have like, so first of all, phi 1 of x itself is just x minus alpha squared. So we can set that equal to y and then invert. So we'll take square root. So yeah, let me explain. If I have this equation here, where y is some given non-negative number, so we can take square roots, but that's going to, of course, require a plus minus. And then we move the alpha over. So x is going to be alpha plus or minus radical y. And you see that alpha plus radical y is greater than alpha. And alpha minus radical y is less than alpha. So the correct inverse for the red piece, which is less than, the domain here should be less than alpha, is alpha minus root y. Okay, and then this other piece, phi 2, it's defined by the same formula, but the domain is different. The domain is x greater than or equal to alpha. And its inverse is going to be alpha plus radical y. So two different like local inverses. Okay, anyway, so we have to think about type 1 versus type 2. But you can see that there are no type 2 terms. It just so happens there are no type 2 terms because every y that's greater than or equal to 0 is going to cut through both the red piece, possibly at its endpoint, when y is 0. Right? When y is exactly 0, the blue line is going to cut through at least the endpoint of the red graph. Okay, and it also cuts through the green piece, again, possibly at its endpoint alpha, in the case when y is exactly 0. But that means that the terms are only type 1. Both terms are type 1. Or to put it differently, both of these intervals are of type 1. So the terms we're going to get is like corresponding to one of those intervals is going to be f of the local inverse minus f of the endpoint, which would be negative infinity for this first interval. This first interval here goes from like minus infinity to alpha. But we don't take the change in f all the way from minus infinity to alpha. We take the change in f from minus infinity up to, oh, I'm sorry, I screwed that up because it's a decreasing piece. Yeah, this first piece, remember, is a decreasing piece. So the correct formula to use in this case for a decreasing piece would be f at the right endpoint, alpha, minus f upper minus at the local inverse. Okay, good. Yeah, that's better. Okay, and then we have another term corresponding to the other interval. The other interval goes from alpha to plus infinity. But that's an increasing piece. So the correct form for that would be f of the local inverse, which is alpha plus radical y, minus f of the endpoint, the left endpoint. And that's going to be the formula in the case, again, where y is greater than or equal to 0. Okay. Now you can see that there's a little simplification possible. There's a bit of a simplification that's possible here because you have f of alpha and you also have minus f of alpha. You may as well just cancel those. And so in the end, what you get is that g of y is f of alpha plus root y minus f upper minus of alpha minus root y when y is greater than or equal to 0. And then 0 otherwise. Y is strictly negative. Okay, and that's it. Now that function is associated with, in a one-to-one fashion, a random variable, y hat, which is the pseudo-inverse of g, restricted to the open interval 0 to 1. And it's that y hat that we call x hat squared. It's the random variable with this CDF. So x hat squared, x hat squared has the CDF given by this formula here. So that's a good way to understand, the square of a variable, the square of a random variable, rather, by looking at its CDF in terms of capital F, which was the CDF of the original random variable. Okay, great. So that's takes care of that topic. Now, what about expected value? We still need to answer this question, like, how do I find the expected value of some function of x hat, such as x hat squared? Okay, and again, what I said here is that there's no general formula for this, for random variables in general, but there are formulas for this in the discrete case and the continuous case. So I'm going to just talk about the continuous case only. And I'm going to leave the discrete case as an exercise, which you should try to do when you have some free time. It's a fairly easy set of calculations, and it follows very closely with what we're about to do. It follows very closely, except that it uses summation instead of integration. So you should easily be able to fill in all the details for yourself just by analogy, by reasoning by analogy. All right, so let's start taking a look at this. So we're going to assume throughout the rest of the video that x hat is continuous, and that phi of x hat, which is a new random variable, is expectable. Actually, no, I don't want to assume that. I want to test how to figure out if that's true. So okay, for now, let's just assume that x hat is continuous, and its density is f. Integration density is little f. Okay, so the first thing I'm going to try to do, well, actually, let's go back for a second and just stare at the formula for capital G. Here it is here, right? So I made a huge mess out of this slide, but if you just look at the black text, just ignore all the colored text, try to focus on that black text, just the formula for G of y itself. Let's ask ourselves, what can we say about this function in the case where big F is actually continuous? Remember, if it's, I should remind you that we worked out this theory for any random variable. Like, we didn't assume that big F had any special properties. It was just a CDF. We assumed it was non-decreasing, right continuous, and exhaustive. We didn't assume that it was continuous everywhere. But in our situation now, we're restricting attention once again to a continuous random variable only, which means that we can look at this formula afresh with the knowledge in mind that big F is now going to be continuous everywhere. Not just right continuous everywhere, but actually continuous everywhere. Okay, so then you can see that these compositions here are continuous, right? Phi sub n inverse is continuous, and F is continuous, so their composition is going to be a continuous function of Y. And then you're subtracting away a constant. So every term of type 1 is going to be a continuous function of Y. Also, by the way, notice that the upper minus here is unnecessary now. Because if capital F is continuous everywhere, then it just coincides with F upper minus. There's no distinction between capital F and capital F upper minus anymore. So you can actually just ignore the upper minus sign when you're working with continuous random variable. But again, the composition is going to be continuous. Phi n inverse is a continuous function of Y, and you're plugging it into a continuous function. So every type 1 term is going to be continuous, right? And then if you look at the type 2 terms, they're just constants. But you have to be a little bit careful because as Y changes, the question is, can you pick up more type 2 terms? And the answer is yes, because if Y decreases, right? You see, we talked about this a little earlier. If Y increases, if Y jumps to some V, which is greater than Y, then that V is still greater than the range of phi n. So all those terms just stay put there. But if Y makes a decrease, then it could go from being greater than the range of phi n to being in the range of phi n, which means you will lose one of those terms. Okay? So, yeah, Y, if you take the value of Y and just decrease it, just like a very, very, very tiny amount, you could still end up losing a positive term from that type 2. Okay? But it doesn't just disappear. It then becomes a type 1 term. And that actually is a continuous change. See, a type 2 term is going to disappear, but you're going to have in place of it a new type 1 term, which will be changing from that type 2 term continuously. How do I know that? Well, basically, either Cn is going to change, let me do that in some color. Either this Cn is going to change continuously to phi n inverse of Y, as Y moves downward. So if like Y has a certain value, and then Y jumps downward, it could be that Cn gets replaced with phi n inverse of Y. But that's a continuous change, because Cn is like the uppermost value of phi n inverse. Cn minus 1 is the lowest value of phi n inverse, and Cn is the highest value. So that would be actually a continuous change. Okay? Or what could happen is that maybe Cn minus 1 gets replaced with this, phi n inverse of Y. But again, that would be a continuous change. So essentially what's going to happen there is, if you make a decrease to Y, the type 1 terms are going to change continuously as long as you make a small enough change to Y. So I'm talking about a very tiny change to Y. You make a really, really tiny change to Y, right? Basically all the type 1 terms are going to stay the same. But what could happen is that a type 2 term might disappear and be replaced by a type 1 term that's virtually equal to it. So the point is that G is actually continuous itself. It's a little hard to see that in detail, to write down a rigorous proof of that. But a good way to gain confidence in this claim is to look at this special example. Let's look at this special example again. Yeah, this one here. And let's now assume that F is continuous everywhere on the entire real line. And therefore this F upper minus can just be replaced with F. Okay, so if that's the case, I claim that this G is also continuous everywhere on the entire real line. Okay, let's think about it. If Y is already positive or non-negative, yeah, there's a couple of things we have to check. Let's say that Y happens to be positive, and we allow it to make a small change so that it stays positive. So since, okay, the change can be in either direction. You can either increase the Y a little bit, or you can decrease the Y a little bit, but stay on the positive side. Well, because we're on the positive side, it's always going to be this formula that applies, and you can see that that formula changes continuously, because, you know, radical Y is a continuous function on the positive side of the reals. And so alpha plus radical Y will be changing continuously, and then F of that will be changing continuously. Similarly, alpha minus root Y and F of that will be changing continuously. Okay? So certainly, in that case, when Y is positive, a small change in Y will lead to a very small change in G. Okay. What if Y is exactly 0? Then a small change will take you onto the positive side, and that certainly will be continuous. Like G will change by a very small amount. Oh, okay, we should figure out what is the value of G of 0. If Y is exactly 0, what is G of 0? Okay, well, you can see what it is. It's actually 0, because it's alpha plus root 0, which is simply alpha, and then here you'll have alpha minus root 0, which is also alpha. And F minus are the same, so it's F of alpha minus F of alpha. You actually get 0, which is nice because it shows it's continuous with this other branch. They join up correctly. So yeah, that actually proves the continuity of G entirely. Oh, well, not quite, sorry. I still have to check that if I approach 0 from the positive side, does the value approach 0? So let's say Y is approaching 0 from above. Then alpha plus root Y is going to approach alpha from above, and alpha minus root Y will approach alpha from below. And therefore F of the first will approach F of alpha, because F is continuous. F of the second one will also approach F of alpha, because F is continuous. And then their difference will approach F of alpha minus F of alpha, which is 0. So you get the correct limit behavior. Not only is G equal to 0 at 0, but G at 0 plus is also 0, has the correct limit. So yeah, G is actually continuous everywhere. And this argument generalizes, like, to the general case. Basically, the theorem that I'm proving here is the theorem that for a function phi of the type described above, meaning, like, you know, it has these alternating intervals where it's alternating, increasing and decreasing, and it's continuous everywhere. That's very crucial. Phi has to be continuous everywhere on the entire real line. Okay, anyways, for such a function of that type, and for a continuous random variable, x hat, the new random variable, phi of x hat, is also continuous. Okay, and it's because you can check that the capital G, right, the CDF, is still continuous. And again, it's like based on a trade-off between type 1 terms and type 2 terms. When you change the value of Y, you could end up losing a type 2 term and then gaining a type 1 term for the same interval. But the type 2 term that you lose and the type 1 term that you gain will be extremely close together if the change in Y is very, very tiny. So the overall change to the function G will be arbitrarily small, as long as you make the change in Y arbitrarily small. Okay, so anyway, you can check out the details of that yourself. There are many, many cases. You know, unfortunately, it's quite messy. You have to look at a lot of different cases, but all the cases work similarly. So if you understand the basic principle that you have this trade-off between type 1 terms and type 2 terms, where you can lose one and gain another for that same interval, and when you do that, the term you lose and the term you gain are very close together. Can be made arbitrarily close together by changing Y a very, very small amount. So that shows the continuity. Okay, now that's unfortunately that's not quite enough, because remember that being a continuous random variable, is not just about having a continuous CDF. The CDF also has to be like piecewise C1. It has to be C1 except on a discrete set. Okay, so let's look back at our example here. If I assume that this f, which is also in this term as well, let's assume that this f is like piecewise C1 as well, so it's continuously differentiable except on a discrete set. But you see that these local inverses are also differentiable. So you're plugging differentiable functions into differentiable function, except at some discrete number of points. So again, because the local inverses, phi sub n inverse, are actually differentiable everywhere, except possibly at the c sub n's, of which there are only discretely many, in fact only finitely many. And because f itself is continuously differentiable, except at discretely many points, the compositions, these compositions of f with the local inverses, will also be piecewise C1. Okay, so it actually still works fine. Capital G of y is both continuous and also piecewise C1 on the reals. And therefore we really do have a genuinely continuous random variable. This is a true theorem here. Okay, I'm going to regard this theorem as having been proved by my comments, although it wasn't a complete proof, obviously, but I just gave you an indication of proof by telling you roughly how the ideas that go into the proof. The actual proof is, a little messy, as I said, it's lots of different cases you have to analyze, but the principles and the ideas are very clear. Big G is continuous because of that trade-off phenomenon, and then also big G is piecewise C1 because big F is piecewise C1, and the local inverses are all piecewise C1 as well. They are C1 except at their endpoints, at the endpoints of their domains. Okay, you're just composing those together. Compositions of piecewise C1 functions are also piecewise C1. Great, okay, so when you go to do this exercise about the discrete case, you should start with a similar theorem for the discrete case. Your theorem should say, for a function phi, right, for a function phi of the type described above, and for a discrete random variable x hat, the new random variable phi of x hat is also discrete. So it's the same theorem except that both instances of the word continuous should be replaced by discrete. And let me just remind you what discrete means, is that the CDF is a step function, a tame step function. So what you essentially have to prove is that if big F is a tame step function, then big G is also a tame step function. And that's not difficult to do. If you stare at the formula for big G, and just keep in mind that big F is a tame step function, you should easily be able to establish that big G is also a tame step function. Okay, anyway, so what about